Hello AP Statistics students, this is Mr. Liao and I'm coming to you live over California, somewhere in an airplane. Alright, I'm sitting in the classroom. So, we're going to be working on section 3.3 today, Residuals. This is the last section in the chapter. We are skipping over one section which we will come back to next week. So, take out your note sheets. There should be 4 pages. I also realized I punched the wrong side of one of the pages. Hole punch, so I'm sorry. But you guys have a hole puncher on the side of the room, and you probably can do it at home. If it bothers you, you can punch the other side. Have a calculator handy. We're going to be using it. If you need to take a break, take a break. I have no idea how long this video is going to go. I'm going to guess. No, I'm not going to guess. So, strap back, sit down, relax, and if you need to stop to go to the bathroom, stop and go to the bathroom. Don't take me with you to the bathroom. That's gross. Here we go. So calculate the residual for a given observation and interpret residual plots. We're going to use the residual plot to see if the straight line is a good model for a bivariate data set, and then we're going to describe the effect of outliers and influential points on linear regression. So let's start with residuals. SSE is the thing we haven't quite learned yet. We're going to come back to it in the next section. But basically the sum of least squares is the sum of the vertical distances squared from predicted y hat to observed y. Remember that vertical line we had? You squared those, you add all those distances up. The least squares regression line is the line where the SSE, the sum of least squares, is the smallest. But because they represent, and when I say they, the vertical distances represent leftover variation in the response after fitting the regression line, these distances are called residuals. Residuals are basically the difference between predicted y and observed y. Here it is. A residual is the difference between an observed value of the response variable and the value predicted by the regression line. That is, the residual is equal to observed y minus predicted y hat, or y minus y hat. So remember, observed always comes first. This is the same formula that we use for the so-called error. We'll come back to that also in the next set of notes. But observed minus predicted. If you were to plot that on a graph, for a positive residual, the observed value would be higher than the predicted value. If you had a negative residual, the predicted value would be higher than the observed value. I think I got that straight. So, take a look at your paper. This is straight from the book, page 167, example 3.14. And I copied the data from 168 onto your paper. And we want to know, at what age does the age at which a child begin to talk predict later score on a test of mental ability? So I want you to enter the numbers from the chart into your calculator. Put the age into list 1 and put their score into list 2. Alright, so go ahead and pause the video while you do that. Alright, so now that you've entered the data into the calculator, and you can pause the video whenever you need to do something. I'm not going to obviously sit here for 2 minutes doing nothing, waiting for you to enter stuff in. So pause, restart. Alright, so on your screen you see an Excel scatter plot and the scatter plot from your calculator. Notice in Excel, when they plot the least squares regression line, it only goes from the smallest x value to the largest x value, which again illustrates the importance of don't extrapolate when you go beyond the domain of x. Anyways, you take a look at the scatter plot and you can see that the association is negative. There is a negative association between the age of first words and the Giselle adaptive test score of mental ability, which makes sense. Children who begin to speak later then tend to have lower test scores than early talkers. The earlier you talk, probably you're going to score higher on a test. If you do your Lin-Reg on your calculator, you get these values, and you can enter the equation of the line, r and r squared. We'll get to r squared on Monday, but now you see our r is negative 0.64, which tells you that the association is negative, and it is moderately linear, albeit not super linear. Alright, so now do the equation of the least squares line, write it down, don't forget to define the terms. I'll wait until you're done. Alright, you're done. So here's your equation. Y hat is 109.8738 minus 1.127x. Y hat represents the predicted score on a mental ability test. X represents the age of child in months. And before you look at this, think, wow, a 15-year-old doesn't speak until he's 15? That's crazy. No, it's months, so it's 1 year and 3 months. Alright, so now that we have the equation of the least squares line, we need to try to predict the score of child 1, which is a child that's first spoke at 15 months. So you take your 15, you plug it into your least squares equation, and you get a value of y hat equals 92.97, which means that we predict that a 15-month-old would score 92.97 on this test of mental ability. Now we have to calculate the residual. It's pretty simple. It's observed y minus predicted y hat. So 95 minus 92.7, which leaves you a residual of 2.03. So the residual is positive because your data point is above the line. Now it's hard to see, but this red block represents the line, and this blue dot represents the data points. So you're going to have a positive residual. Now let's try to do this on your calculator. Turn over your note sheet. To find all the residuals, run linreg number 8 as you have before. Put L1 for X list, L2 for Y list, and Y1 for your storing your regression equation. Plot the scatter plot and the least squares regression line, which I showed you on the previous screen. Now, in the list editor, highlight list 3. You have to do this part first, otherwise this part won't work. Press enter to go to list, which is the second step button, and scroll down to resid. Press enter twice and you should see the list of residuals in L3. So there it is. Enter that in, change that screen, hit return, and there it is. And you can see the residual list is 2.031, which matches the residual we got on the previous screen. Alright, I decided I'm going to add this little bit into the video to show you how to do it on your calculator, just because I'm afraid you guys might have missed it. Alright, so I have my lists in L1 and L2. L1 contains the age of the child at first language or first words, and L2 contains their score on this mental test. Now, let's run linreg to get our values and to get our residual. So, let's get out of here by quitting. And because this calculator stinks, I need to turn diagnostic on every time. So scroll down, or press D, turn diagnostic on, and this will allow you to display R and R squared. Alright, now let's do the linear regression. So go to stat, then go to calc, scroll down or enter number 8, which is linreg A plus BX. And for the X list, we'll have L1, which is the age of child. Y list will have L2, which is their score on this test. Leave the frequency list blank. In store regression equation, let's put in Y1. So go to vars, go to yvars function, Y1, press enter and calculate. Whoops, did it twice. And there is the thing we got on the screen. Now, you notice that we have R squared, we have R, we have A and B. But we don't have residuals. Well, there are a couple ways to find the residual list. One, you go to your stat list, and if you scroll all the way to the right side, you will notice there's a new list. Oh, it's not on mine. Well, that's okay, because if it's not there, you can bring it up. So on some of yours, you can scroll to the right side, and you will see a residual list in this column. If not, that's okay. What you're going to do is follow the directions I have on the paper, which is go to L3, highlight the name, and now let's bring out the residual list. Now go to your list of lists, which is second stat or the list button, and there it is. Go to resid, hit enter, and looky here. We have the list of all the residuals. Now you will notice that the first residual for child 1 is 2.03, which is exactly what we got when we did it by hand. Alright, that's enough for the calculator. We'll come back to the calculator in a bit. Okay, let's move on. Residual plots. A residual plot is a scatter plot of the regression residuals against the explanatory variable or against predicted y-hat values. Residual plots help us assess how well a regression line fits the data. Again, they are going to assess us how well a regression line fits the data. Now, how do we use this? And again, if I'm going too fast, stop the video. The sum of the least squares residuals is always 0. If you add up all the residuals, they add up to 0. Now, when you do this on your calculator, you may not get 0 exactly because you're going to get something called round-off error because you're not going to get it perfectly to 0 sometimes. Since the sum is 0, the mean also has to be 0. So the mean of the residuals is also 0. Now, you can check this on your calculator. So, let's take a look. On your calculator, I'll use screenshots first, then I'll go back to the calculator. So, assuming you have your residuals in list 3, use one variable stats on list 3, and you will bring up this set of numbers. Now, the sum is basically sigma x, the sum of x. So you can see the calculator showing some round-off error, but this number is pretty much 0. It's 8 times 10 to the negative 11th, which is an 8 with 10 zeros behind it. So it's pretty close to 0. That's how you can use your calculator to check it. Alright, so here's the live picture of the calculator to check the sum of the residuals. You have your list of residuals in list 3 if you haven't changed it. So let's get out of here and let us run one variable stats for the residual list, which is L3. Hit calculate, and there's the screen. You want to look for the sigma x, which is the sum of all the observations in that list, and you get a very, very small number, 8 times 10 to the negative 11th, which is practically 0. So that's how you check the sum of the residuals using your TI. Alright, now how do we know if residuals make a good summary of the data? Well, how do they tell us if there's a good summary of the data that's linear? So we want to identify a good fit. So this is an example of a residual plot. You notice that the x is on the x-axis and the residual is on the y-axis. And this is basically how far the predicted value is from the observed value. So, a couple things. If the regression line captures the overall relationship between x and y, the residual plot should show no obvious pattern. Okay? Again, you have a random scatter of dots on the residual plot. If you have a random scatter, that's good. And that means the regression line actually captures the overall relationship between x and y. We'll get to that more in a second. Number 2, the residuals should be relatively small in size. So, they should kind of form a narrow band as x goes from the small values to the big value. If they start to get really big, that's a problem. So what you want to see is a narrow band of random dots appearing around the 0 residual level as x goes from whatever the small value is to the large value. So let's take a look at some examples. This is unstructured scatter, random scatter. An unstructured scatter of residuals indicates that the linear model is a good fit. This means if you see a random scatter of dots on a residual plot, remember this is a residual plot, that's good. That means the line that you used to calculate predicted values is probably a pretty good predictor of what y it would actually be if you plugged in a value of x. So that means the linear model is a good summary of data. It's a good fit. That's good. Now, if you have a curved pattern, that will indicate to you that the relationship is not linear. So if you see a curve or any other sort of distinct pattern, that tells you the relationship is not linear. Thus, the linear model is not a good summary for the data. You would not use the least squares regression line to describe or predict values of y given values of x. So again, random scatter, good for linear regression. Curved on a residual plot, not good. The other thing that's not good is to see increasing or decreasing spread about the 0 line as x increases. This indicates that the prediction of y will be less accurate for larger values of x. Again, if this is the case, the linear model is not a good summary for the data. So you notice that x is small, there's a very small residual. But as x gets larger, the residual gets larger and larger. This is a problem because as you get to really large values of x, you find that your linear regression model is not at all accurate enough. So again, you do not want to see an increasing band or a decreasing band. You want to see the height of the plot be narrow and be even from all the way to the left to all the way to the right. Now to plot residuals on your TI, this is how you do it. Turn off plot 1 and turn off the regression equation, which means go to y equals and delete that equation. Now what you're going to do is make a scatter plot using plot 2, using L1 as the x list and L3 as the y list. L1 is your x values, L3 is your residual list. Then hit zoom stat or zoom 9 to plot it. So if you did it correctly, this is what your residual should look like. Alright, let's do this on the actual TI so you can see it live. That was our one variable stats. Let's clear and follow the directions on the paper. It says what we need to do is turn off plot 1. So let's go ahead and turn off plot 1. Hey, it's off. Huh, great. Now let's turn on plot 2 and select scatter plot. Now for your x list, you're going to use L1 and you're going to use L3 as the residual list, which I hope is still in my calculator. Otherwise, you will never see this because it's going to be re-recorded. Alright, now the other thing you have to do is make sure you turn off your regression equation, which I forgot to do earlier. So go to stat plot, or go to plot, just y equals. Here's the regression line. We don't want that there, so let's get rid of it. Now let's do a zoom 9. And there is our residual plot, which matches what's on the paper. So to do a residual plot, do a stat plot, use x as list 1, use the Y list as L3 or whatever your residual list is, clear any regression line, and then use zoom 9 to plot the graph. Alright, let's look at the degree days and gas examples. So, if you have a calculator, bring up the degda list and the gas list and put them on two lists. You can use L4 or L5, it doesn't matter. And what you're going to do is try to replicate the residual plot that you see on the paper. So the first thing you need to do is to use linreg to create the residual list. What linreg does, every time you run it, it creates a new residual list. So if you're going to use a new set of data, you have to rerun linreg. And you must answer the question, is the linear model a good summary for the data? So go ahead and try it and see what you come up with. Alright, so this is the screenshot you should have. Now we have to answer the question, is the linear model a good summary for the data? And if you take a look at the pattern, well, I mean, you have some high values here and there, but as x gets bigger, the band of residuals doesn't get that much wider, and we don't have that big of a data set. So we don't see a curve. We see what appears to be pretty random scatter. So we will conclude, yes, it is a good model, good summary for the data because there's really no overall pattern to the residual plot. And now I'm going to show you how to do it on your calculator after some editing. Alright, let's go back to the TI. I've already put in the degree days list into list 1 and the gas list into list 2. So now let's try to recreate the residual plot. The first thing you need to do is make sure that everything is clear. So that's clear, that's good. Let's go to linear regression. So go to calc, scroll down to linreg, and on my calculator it's L1 and L2. On your calculator it might be different. I'm not going to store the regression equation for now because I don't want to have to delete it later. So let's calculate it, and that's the familiar numbers that we've seen several times. Now let's make the residual plot. So you're going to want to go to stat plot, and I'm just going to use plot 1 for the head. I'll use plot 2 since it's already on. So L1 is the X list, L3 is the Y list. If you're not sure if it's there, go to stat, edit your list, and well, I should probably put it in there. So make sure you put the residual list into list 3. So go down, there's resid, put it in, and bam, there it is. Now, we'll go to stat plot. We'll use plot 2 because it's already ready to go. All the parameters are correct. Zoom 9, and there it is, the plot that matches the plot on your paper. So, make sure you run linear regression to create the residual list, and then make sure you go back to your stat list and load the residual list into one of the numbered lists, and then use that list to plot your data. Alright, here's another example. Because I ordered this originally differently, it's not going to be on your sheet, but let me give you the setup. Some people don't gain weight even when they overeat. Don't you hate those people? Yeah, I know. Perhaps fidgeting and other non-exercise activity, or NEA, explains why. Some people may spontaneously increase NEA when fed more. Researchers deliberately overfed 16 healthy young adults for 8 weeks. They measured fat gain in kilograms and the change in non-exercise activity, fidgeting, daily living, and the like, and the numbers are reproduced on your note sheet. What I want you to do is use linreg to create the residual list, redo the list, and tell me if the linear model is a good summary for the data. So go ahead and do that, and come back and restart the video when you're ready. Alright, let's take a look. So this is a scatter plot you should have. It matches what is on your paper. Now we must ask the question, does this residual plot tell us that the linear model is a good summary for the data? And the answer is yes. Here we really have no overall pattern. You have some high, you have some really close, but it's not discernibly different. And we don't, again, have a lot of data points. We have 16. But because there's no curve, it's not getting bigger, we have no overall pattern. It appears that the linear model is indeed a good summary for the data. Alright, so let's try to do this with our calculator. I had the list entered in, and so hopefully you did it as well. First, we need to create the residual list, so let's do some linear regression. So let's use stat calc. I'm going to jump to 8. L1, L2, don't need to store the equation this time, so let's calculate it. Whoops, did it twice again. There it is. So you see our R is negative 0.78. There's our AB. Again, we're doing this because we need this to happen to run the residual. So let's go to our lists, and let's go to L3, and let's bring up the residual list. And there it is. Now let's do our stat plot. Stat plot, I'm going to use plot 2 because it's already there. All the parameters are correct. Let's give ourselves a zoom stat, and there's the plot that matches the one on your paper. So again, you can see that there is no discernible pattern. It's random scatter. It doesn't curve. It doesn't get bigger. It doesn't get smaller. It's pretty random. So this tells us that the linear model is indeed a good summary of our data. Alright, one more example I'm going to make you do before we move on to the next topic. The stupid backpackers again. So, bring up those 8 numbers, put them in, and ask ourselves, what about the residual plot for our backpackers? Is the linear model a good summary for the data? Go ahead and do this and see what you get. Alright, here's our data plot. And the question is the linear model good? Well, it's not a very big data set, only 8 observations, but it does look like that as X is getting bigger, we have a few points out here and here. So the spread is increasing. So it turns out the linear model may not be the most accurate. And now I'm going to show you how to do this on the calculator. Alright, I've got the backpacker information entered back in. So let's bring up the residual plot. Go to Stat, Calc, LinReg, and L1, L2. Calculate. There's our regression information. Look at our R is 0.795. We did that before. Now let's go to our list and bring up, whoop, that's not the right one. Stat, edit, L3. Let's bring up the residual list. There it is. And there are our list of residuals. Now let's do a stat plot. Plot 2 is still the one on my calculator. Zoom 9. And there is our residual plot. And again, you can see the increasing spread as X goes from smaller to bigger. So that ends our discussion on residuals. Again, a residual is the difference between the observed value of the response variable and the predicted value. And you can find the residuals by using linreg on your calculator to create a residual list in your calculator's memory. Then you will go to your list editor, pick an empty list, bring up the residual list and save it into one of your lists. Finally, you will do a stat plot using the X value in your original scatter plot and using the Y list as the list of residuals. And what you want to do is read what the residual plot looks like. And you want to see an unstructured random scattering of points around a narrow band of 0. That will tell you that the linear model is a good fit. The residual plot, again, tells you whether the linear model is a good fit. And again, you will also look at the scatter plot. The original scatter plot will give you an indication as well. If you have a curve, a pattern, or the spread of the residual is increasing or decreasing as X gets bigger or smaller, that will give you an indication that the linear model is a below average or inaccurate model for the data, and you might have to consider a different model. So let's move on to our final topic, outliers and influential points. This is on page 13 on the page where I copied or punched the holes on the wrong side. So an outlier is what you think it is. It's an observation that lies outside the overall pattern of the other observations. We saw them with single variable data. We'll see them with bivariate data. And first, let's take a look at that scatter plot on the top of page 13. First of all, we have individual points with large residuals. These are outliers in the vertical y direction because they lie far from the line that describes the overall pattern. So here is the 0 residual line. Some are very close. Most of them are very close. But then we have this guy up here. This is child 19. This is the kid that didn't start speaking until 17 months, which if you look at the different ages, it's on the higher end. But his score was 121, which was the highest score among all 21 kids. This tells you that our predicted score for this child was about 30 points too low. So, this is an outlier in the vertical direction. So child 19, his residual is high. This is a vertical outlier. We also have individual points that could be influential. An observation is influential for a statistical calculation if removing it would markedly change the result of the calculation. So by taking away that point, you would change perhaps the R value, you would change the slope, you would change the direction of the line. All those things would change if you remove this point. That will make a point influential. Points that are outliers in the X direction of a scatter plot are often influential for the least squares regression line. And if you take a look at the example and that scatter plot, let's see if we can find one. So individual points that are extreme in the X direction tend to affect the least squares regression line. Child 18, right there. Hello, where are you? There you are. This is the child that didn't start speaking until 42 months, more than twice or almost twice the age of any other child. Unsurprisingly, his score was the lowest of all 21 kids. Now, this point tends to really affect the least squares regression line. Now, if you go to example 3.14 on the second half of the page, you're going to see why. Here's our original data. You take a look at your AB, go ahead and re-up those numbers, put them into your calculator, rerun the regression, and you will see these points. Very good. Now what I want you to do is remove child 19. So go to your list, take out the child that has a 17-month age and a 121-point score. Take those out, and I want you to see what that does to R, as well as the data. And I'll give you a second to do that. Don't cheat. Go ahead and try it. Alright, so if you've done that, you will see that here's the data without child 19. Well, our R value has gone from negative 0.64 to a stronger negative 0.75. This makes sense. Outliers tend to affect the shape of the distribution, affect various measures. Although you notice our slope didn't really change that much. It was negative 1.14. Now it's negative 1.19. But our R, which was negative 0.64, is a little stronger at negative 0.75. So that's what removing the vertical outlier did. It changed it a little bit, but not a whole lot. And if we go back and forth, you will see it. Getting dizzy? Good. Alright. Bam. Alright, now let's go ahead and do the last question. Now, put the child 19 back. Put back 17 and 121. You can just put it at the bottom of the list. And now remove child 18, original child 18. Remove the child that has an age of 42 and a score of 57. And I want to see how does that affect R. And on your paper it says how to remove in child 1. It should be child 18. So go ahead, do that. Rerun the linear regression, look at the scatter plot, and tell me what you see. We're removing this dude out here. Alright, restart the video. Here we go. And if you take a look at the difference, wow. Well, the line's a lot shorter, which makes sense because now your domain of X is a lot narrower. But take a look at what happened to R. It went from negative 0.64 to negative 0.33. That's a huge difference. Take a look at the slope of the line. It went from negative 1.127 all the way down to negative 0.779. So this really shows the influence that a point that's extreme in the X direction can have on R, on the slope, and on other values in the data. So look out for outliers, really look out for influential points, and consider what that point does with the data. If you remember our worksheet, you remember the elephant. He was way out there. He weighed more. He had a bigger brain. But that made the graph much more linear than it probably was. You remove the elephant, and you'll probably have a weaker relationship, but one that's more accurately predicted. Alright, thanks for hanging in there. That's the end of this. If you have any questions, post them on Facebook. Please email me. I will come back on Monday, but you should have problems to work on Friday in class. So if you didn't watch this video and you got problems on Friday, well, guess what? You got to watch the video at some point or read the book. See ya.